First, are there questions from yesterday's lecture? Sure there are. Oh, there aren't. Very good. Anybody else? Okay, so let's start where we left off yesterday. So last time, we discussed the Dirac algebra, and we derived it the way Dirac had derived it himself. And we showed that the Dirac algebra implies there exists in 4 space-time dimensions 2 pairs of creation and annihilation operators which satisfy this anti-commutation relationship amongst other relationships. And based on a discussion we had earlier in the class, this implied that the gamma matrices are 4 by 4 matrices, not 16, and that the Dirac spinor is a 4-dimensional object. What we did then is we said that we are going to promote the Dirac spinor, which was constant, to be a function of space-time. And we then made the assumption that under a Lorentz transformation, the Dirac spinor transformed in this way where if we assume that the generators of this representation are given by the commutator of the gamma matrices, then using an identity, one can show that these guys satisfy the Lie algebra of the Lorentz group. So they satisfy the Lie algebra of the Lorentz group, the orthochronous proper Lorentz group. Okay? We then made a comment that the Lie group, the Lorentz group, is actually a non-compact Lie group, and that's because the rotations are compact, but the boosts are non-compact. And there's a theorem in group theory which says that non-compact Lie groups do not have finite dimensional unitary representation. Okay? And based on this theorem, we concluded that because the Dirac representation is 4-dimensional, so these guys are 4-dimensional, therefore it cannot be a unitary representation. And that's reflected in the fact that these S matrices, these are what we are calling S lambda, these are not unitary. So if you take the dagger of this, this is not equal to its inverse. Okay? Then we ended with the question whether the Dirac representation is reducible. So, is the Dirac representation reducible? To answer this question, which we will answer today, I want to invoke Schur's lemma, which is a theorem from group theory. And Schur's lemma says that if a matrix commutes with all the group matrices of an irreducible representation, then this matrix is proportional to the identity matrix. Okay? So to show that the Dirac representation is reducible, we have to find a matrix which commutes with all the matrices of the Dirac representation, but which is not identity. So I'm kind of giving away the answer, the punchline, but you probably already know the punchline by now. So such a matrix can be constructed, and let's call it gamma 5, and it's a historical label. It's defined so this implies, if you just do the algebra, it's just one line. The sign of gamma 5 is conventional, so I chose a minus sign. You will see some guys, some authors choose plus sign. Now, the important properties of gamma 5, the most important property for our purpose is that gamma 5 anti-commutes with all the Dirac matrices. Now, this implies that gamma 5 cannot be an identity matrix, right? So gamma 5 cannot be the identity matrix. Otherwise, it would just commute with everything. So gamma 5 is Hermitian, and the I here does that job. And gamma 5, if you square it, you get the identity matrix. Now this implies, very importantly, that the eigenvalues of gamma 5 are plus 1 or minus 1. Okay? Now I want to ask you a question. The question is now, is the Dirac representation reducible or irreducible? You can discuss amongst yourself. Let's just take a minute. How would you think about that? And I'll give you a hint. See if you can answer this question. Can you see that board? Okay, let's try something else, okay? Is this better? Oh, that's too dark. Let's bring it down then, okay? Then maybe you can see it. Is it better? All right. Have you guys come to a conclusion? What say you? We need a volunteer.
Reducible.
Reducible. Why?
Gamma 5 commutes with all the generators, so it commutes with all the group elements.
Okay, good. So that's correct. Fear has given us the right answer. Observe that gamma 5 anti-commutes with all the gamma mu's. The generators are quadratic in gamma mu's and antisymmetric, and therefore gamma 5 must commute with the generators, right? So this is 0. And then it follows that it will commute with all the matrices of the representation. So the Dirac representation is reducible, which means that there exists some basis in which the Dirac matrices take like this block diagonal form. So these are 2 by 2, and these are 2 by 2 zero matrices, okay? And one can show, although I don't know how to, that you cannot reduce it down to even smaller representation. Okay? So you can think of the space of spinors, the space of Dirac spinors, as this big vector space. So this is the Dirac spinor space. And it divides into 2 subspaces, subvector spaces. And one of the vector space corresponds to the gamma 5 eigenvalue -1. The other vector space corresponds to the gamma 5 eigenvalue of +1. And the subspace which corresponds to the gamma 5 eigenvalue of -1 is what we are going to call a left-handed Weyl spinor space, and the subspace with the gamma 5 eigenvalue +1 is a right-handed Weyl spinor space. So the Weyl spinors are the irreducible representations of the spinor of the Lorentz group. They are the irreducible spinor representation, okay? And then you can construct projection operator. So this is the projection operator which acted on a Dirac spinor, gives you a left-handed Weyl spinor. So this guy maps you to this. So if you take a Dirac spinor and project it by this guy, then you get a left-handed Weyl spinor. And there is another projection operator, let's call it PR. And this is given by the identity plus gamma 5. The right-handed Weyl spinor is, you project down to the right-handed Weyl spinor space by applying PR to the Dirac spinor. Okay? So all of this has been a little bit abstract. As physicists, we don't like things to be abstract. Those are mathematicians' job, to be abstract. So we want an explicit representation of all this. So there is a basis in which the gamma 5 matrix is block diagonal, is diagonal actually, and it's known as the Weyl or chiral basis. So gamma 5 has this form in that basis. So, I'm not going to write this explicitly in the future, but these are 2 by 2 unit matrices, okay? Identity matrices. So the basis in which gamma 5 takes this form is known as the Weyl basis or the chiral basis. And in this basis, the Dirac matrices take a very nice form. They take nice forms in every basis. We introduced the sigmas in the tutorial yesterday. What are these sigmas? Sigma mu is a collection of 4 matrices. Sigma 0 is just the 2 by 2 identity matrix. This is sigma 0. And sigma 1, 2, 3 are the Pauli matrices. Okay? And sigma bar of mu is similarly, the sigma bar 0 is again sigma 0. Sigma, the identity. But the sigma bar ijk is the negative of the Pauli matrices. Okay? So this notation, it mimics the covariant kind of notation, but it allows us to write the Dirac matrices in this compact form. Otherwise, you would have to write gamma 0, gamma I differently. And it's actually worth doing that. So gamma 0 takes the form of this form, and gamma i's, 1, 2, 3, they take the form. Right, there's a minus sign here. So, given the Weyl basis, we can actually now derive how the left-handed and the right-handed Weyl spinors transform under the Lorentz transformation. And how do we do that? Well, we do that by writing out everything in the Weyl basis. Now, it's given in the notes, but I won't give you a more explicit formula. The generators of the Dirac representation also take a block diagonal form. It must be so, because otherwise these matrices would not take the block diagonal form. So now if you use this explicit expression and work out how the Dirac and, okay. Look at the explicit expression of how this equation looks in the Weyl basis. Then you get the following result. So in the Weyl basis, the Dirac fermion, the Dirac, spinor, will take this form. You can express it in terms of smaller 2-component spinors. Okay? So chi of L is a 2-component spinor. Psi of R is a 2-component spinor. Because we are in the Weyl basis, this is the left-handed Weyl spinor, and this is the right-handed Weyl spinor. Okay? So if we now apply the projection operator on this guy, then we would get the left-handed Weyl spinor would be chi L 0. Right? It would kill the psi R. And similarly, psi R would kill the first 2-component spinor and just give us this guy. Okay, so now using these facts, what we get from this, the way that the Dirac spinor transforms, that psi L. So from now on, when I mean psi L, I will mean basically a 2-component spinor. So it'll become clear from the context whether I mean like a 4-component spinor with the 2 of the thing projected out, or I actually mean 2-component spinor. Okay, let's just not do that. But in the future, I might just use the notation where I just write psi L, but you should think you should have to figure it out whether I mean this thing or this thing, depending on the context. But if there's a confusion, please interrupt me, okay? So from this equation, we now find out that chi L transforms like exponential of minus beta dot sigma by 2, and beta are the parameters of the Lorentz boost, minus I theta dot sigma by 2, and thetas are the parameters of rotation acting on chi L. And on the other hand, psi r transforms like exponential of, and there's a very important sign difference here, plus beta dot sigma. So this is like a three-dimensional dot product, minus I theta dot sigma by 2 psi of r. Okay, this is how these two things transform. So this representation, the Weyl is a left-handed Weyl representation. So this is the left-handed Weyl representation. In the literature, this is also known as half comma 0 representation. And this is the right-handed representation. And in the literature, it's always sometimes referred to 0 comma half representation. The two Weyl representations are inequivalent, which means that if you take these matrices, there is no similarity, unitary similarity transformation, which will take you to these matrices. They are inequivalent. However, they are related by complex conjugation. And you can verify that if you take the left-handed Weyl representation and complex conjugate it and multiply it by sigma 2, this actually acts like a right-handed, this is a right-handed Weyl spinor. Okay? More details are given in the notes. The Dirac, in this language, the Dirac representation in the mathematics language is a sum of these two representations. Okay? And if you are mathematically minded, you can even show that the vector representation is actually comes from something like this. In some sense, the spinor, the Weyl representation are the most basic objects. Spinors are even more basic than vectors and scalars because you can make up vectors and scalars out of spinors, but you cannot go the other way. Okay? And we'll see examples of that. So I want to give you some like take-home discussion problems. And so I encourage you to discuss this problem amongst yourself. It will hopefully deepen your understanding of this algebra. So take-home discussion. And the questions are, suppose you were in 5D. Suppose you were in 5D space-time. Okay? What is the dimensionality of the Dirac representation? The other thing is Dirac representation in 5D reducible to Weyl representations. Okay? Is there an analog of a left-handed and a right-handed? So these are things that I want you to think about. So for the rest of this lecture, I think my lecture notes were a little bit too ambitious. I don't think I can cover everything there. So I will scale down. The lecture notes are kind of the upper limit of things that we want to know. But what is going to be examined in your interviews are things that I will talk about mostly in class. Okay? So, and if I ask you a question which was not addressed in the class, in the interview, you have all the right to kind of correct me. Okay? Or remind me. So, our lesson objectives for this lecture we want to construct Lagrangians which are Lorentz invariant for the Dirac spinor and the Weyl spinors. Okay? And I want, if time permits, I want to introduce a third kind of spinor, which is kind of an extension of a Weyl spinor called Majorana spinors. Majorana spinors are all the rage in condensed matter systems these days. Okay? Okay, I guess people are done with that board now, so I can raise it, hopefully. All right, let's start with an exercise. I want you to discuss a question amongst yourself. The question is psi dagger psi Lorentz invariant? So let me give you some context. So we know that psi transforms, or the Dirac spinor transforms. By the way, this minus sign is conventional. And then psi dagger then should transform in this way. So let's take a few minutes, say 3 minutes, and discuss this amongst yourselves and come to a conclusion whether psi dagger psi is Lorentz invariant or not.
Transform like this. So these are the same matrices that you can clearly put them in the same exponent, and then you will have something like this.
What do you think?
Well, we want it to be positive. Yeah. So we want this to be 0.
What do you mean?
So we would need to require this to be Hermitian.
Great. Do you think it is Lorentz invariant, side-Dagger psi?
We know that phi is
So if you sandwich, what would happen? Would this guy cancel that guy?
No, what do I?
If I have
So just
so side-Dagger psi, we'll go through, say, S of lambda of psi, and this will go to side-Dagger, S of this dagger. So is this equal to side-Dagger psi? So what would you need for that?
exactly. Yeah. We knew, like he said. So
So it's a real
Right. So, which means that S dagger needs to be equal to S inverse, right? Is that true?
and then it's changed to plus.
S is those matrices, the exponential. So are they unitary matrices? Is the Dirac representation? That's something I told you, right? You haven't really proved it yet. Okay, let's prove it, okay? All right, we need an answer, but somebody else, then what do you guys think?
no.
Sorry? No? Okay, why?
We're thinking that that these transformations are not unitary transformations.
Right,
So if you like just glue them together, they wouldn't cancel.
right, okay. Yeah, that's very good. So the idea is that if we now compute psi dagger psi, then this is S, and this is S dagger. So psi dagger psi will go to psi dagger S of psi. But these matrices, as we shall show right now, shortly, are not unitary, so this is not equals to 1. So to show this, basically, if these guys were Hermitian, then of course this matrix would be the inverse of this matrix. So we just have to show that this matrix is not Hermitian. Okay? So, so this is I by 4 gamma mu gamma nu, and then I take away these brackets. Now Hermitian conjugation reverses the order of matrices. So inside the commutator, I will have gamma nu dagger, gamma mu dagger. Now recall that gamma 0 is Hermitian, but gamma I is anti-Hermitian. So if I use this fact here, then you can see that gamma 0I, which are the generators of the boosts, they are anti-Hermitian. Okay? Let's just do it more carefully. So it's I by 2, 0. This becomes, the mu is 0, and this is I. So I of dagger, right? So this doesn't give me a minus sign, but this gives me a minus sign. So I get I by 2, but this is antisymmetric. So if I change the order, I get another minus sign. So we see that this is equal to minus of 0I. Similarly, you can show that sigma ij, the generators of rotation, they are Hermitian, but a generic S, matrix S is not Hermitian. The rotation subgroup is Hermitian, but when you include the boosts, they are not Hermitian. Okay? Now, these Hermicity properties can be encoded in one equation, which is this one. So from this, you can then show that if you take any of the generators and take its Hermitian conjugate, you get the original generator back, but sandwiched between two gamma zeros. And this has to do with the fact that this is quadratic in gamma mu. So this means that this equation can be shown to be this times exponential plus I by 2 omega mu nu. Now there's a gamma 0 here, sigma mu nu, another gamma 0 here. Now if you do a Taylor expansion of this, and using the fact that gamma 0 squares to 1, you can actually just pull this out of this matrix. Okay? So this inspired Dirac to define what is now known as the Dirac conjugate. So if you look at that last equation, you see that if you define a conjugate spinor, this is known as the Dirac conjugate. So Dirac conjugate of psi by multiplying it by gamma 0 on the right, then psi bar transforms in the following way. So psi bar is, how does psi dagger transform? Psi dagger transforms like this. So there's a psi dagger, then there's a gamma 0, and there is the exponential of I by 2 omega mu nu, sigma mu nu, gamma 0. And now there's an additional gamma 0 here. So this is gamma 0 squared, but this thing is 1. And this thing is just psi bar. So this becomes psi bar S inverse lambda. So we conclude that psi bar psi under a Lorentz transformation remains invariant, whereas psi dagger psi doesn't. Okay? So this is a Lorentz scalar. So now I want to construct other type of objects out of a Lorentz, out of spinor bilinears. It's convenient to organize these objects according to how they transform under parity. So I'm going to, we're going to come back to discrete symmetries in the next lecture to do a more thorough job. But today I'm just going to introduce parity so that we can organize the Dirac, the Lorentz covariance. So in quantum field theory, discrete symmetries play an important role. In particular, there are three discrete symmetries known as charge conjugation, parity, and time in reversal. They play a very central role because of a theorem known as the CPT theorem. And the CPT theorem says that any relativistic quantum field theory must be invariant under CPT. Bad things can happen if it's not. The CPT theorem doesn't tell you that it has to be invariant under C or P or T. C, P, or T can be individually broken, and indeed it is in nature. It came as a great surprise. Both P and CP are broken, and therefore T is also broken. And you will see some of this phenomenology in the future class, standard model class. So here we want to organize Dirac bilinears under P, but before we do that, we have to figure out how does a Dirac spinor transformed under parity. Okay, so the question I want to ask is, how does psi transform under parity? So to do this, we do a kind of a quantum mechanical analysis of the Dirac equation. So if I write the Dirac equation in the Weil basis, then it looks like this. So this is the Dirac operator, and it's acting on a Dirac spinor, but I'm expressing everything in Weil basis. So now let's look at the plane wave solutions. So if you look at the plane wave solutions, that means you look at these guys as e to the power I p dot x, where p is the four momentum vector. Then this equation in momentum space looks like this. It becomes two equations. This is the three momentum vector P dotted with the Pauli matrices acting on psi r times m times chi L E plus So an interesting thing to notice is that Dirac equation couples the left-handed Weil spinor to the right-handed Weil spinor through the mass term. Now suppose you were taking the massless limit. Okay? If you take the massless limit, then what happens is that these two guys become decoupled. There's an operator in quantum mechanics known as the helicity operator. And the helicity operator is just the projection of the three momentum, or the projection of the spin of a particle along its three momentum. So this is the helicity operator. The left-handed Weil spinor is an eigenstate of gamma 5, and the right-handed Weil spinor is also an eigenstate of gamma 5. These eigenstates are called chiral eigenstates. So this is sometimes known as the chirality operator. So we can see that in the massless limit, the left-handed Wald spinner is an eigenstate of the helicity operator, and the right-handed Wald spinner is also an eigenstate of the helicity operator. So in the massless limit, the chirality eigenstates and the helicity eigenstates are the same. Okay, they become identical. Okay, why all this song and dance about helicity and chirality? Parity, so okay, let's just, so in the massless limit, so when m goes to 0, helicity and chirality eigenstates are the same. I guess chirality is a Latin or Italian word for handedness. Now, under parity, the helicity of a particle flips. And there is a physical example that I give in my notes using a mirror and things like that. A parity is actually just reflection plus a rotation. A more shortcut way of seeing why parity should flip the sign of helicity is to notice that parity doesn't change the spin of a particle. And that's because the parity matrix, which is 1, minus 1, minus 1, minus 1, that commutes with the rotation subgroup. Okay? But the momentum, the direction of the momentum is reversed under parity. Therefore, it'll flip the helicity state of a particle. Okay? However, if the particle is massless, okay, this is something I should have said before. When the particle is massless, its helicity is an intrinsic property of the particle. And why is that? That's because suppose a particle, a spin half particle is propagating in a certain direction, and you want to flip the helicity. What would you do? You want to boost your reference frame, where its momentum is now opposite, but it's spinning in the same way. Then its helicity would change. It would go from +1 to -1. But if the particle is massless, then there is no such reference frame. There is no such boost so that you can overtake the particle. And therefore, for the massless case, the helicity of the particle it's an intrinsic property of the particle. It's not something that is dependent on the reference frame. It may be that there might be some interaction in which the helicity might change, but as long as that's not happening, the helicity is an intrinsic property of the particle. Okay? Anyway, I just wanted to mention that. But let's come back to what parity does. So what parity does is that it flips helicity. And in the massless limit, because helicity and chirality are the same, it also then must flip chirality. So in the massless case, we expect a left-handed Wald spinner to flip to a right-handed Wald spinner under the action of parity. So all of this to motivate that under parity, we would like the Dirac spinner to transform in this way. Why? Because recall that gamma 0 in the Wald or chiral basis has this off-diagonal block form. Therefore, if you apply it to a Dirac, so if you apply it to the Dirac spinner, which has in the chiral basis takes this form, then it flips this guy and this guy. Okay? So this little diversion is to motivate this relation. Okay? All right, so we can now move on. So let's, so under parity, we expect, so the Dirac spinor to be taken to, of course, because parity reverses the spatial directions, the spatial dependence picks up a minus sign, but I'm going to leave that implicit, okay? So if that is the case, then this thing transforms like this under parity. And that's because gamma 0 is Hermitian. So now we can define a scalar. We've already seen this. A scalar is an object which, of course, transforms like a scalar under the orthochronous proper Lorentz group, but under parity, it remains invariant. So let's see if that is the case. So gamma, so the Dirac conjugate is this object. So under parity, it should, is this object. Under parity, this guy should pick up a 0. Nothing happens to the gamma 0 because that's just a matrix, constant matrix. And psi would pick up another 0. So we've got 3 gamma zeros here. 2 of them will give me 1. So I see that this thing doesn't change under parity. So a scalar under parity transforms like this. There are quantities which are known as pseudoscalars, which under parity transforms in a different way. So if you sandwich gamma 5 between a Dirac spinor and its conjugate, then if you do a Lorentz transformation, a proper orthochronous Lorentz transformation, you can show that this is a scalar under Lorentz transformation. And that's because you'll have to basically write down those S's, and you know that gamma 5 commutes with those S's, right? Because that was the whole point behind claiming that the Dirac representation was reducible. So the S and S inverse that you would get here, they would just go through gamma 5 without any effect and annihilate each other. So this thing, under the proper orthochronous Lorentz transformation, just acts like a scalar. But when you apply parity to it, what happens, there's a gamma 0 picks up psi dagger picks up a gamma 0. There was already a gamma 0 here from the definition of psi bar. And there's a gamma 5 here, and this picks up a gamma 0 and this. These guys anti-commute, so they pick up a minus sign, and then they become 1. So this becomes minus psi 5 of psi. So a pseudoscalar is an object which, under the proper orthochronous Lorentz transformation, transforms like a scalar, but under parity picks up a minus sign. Okay. So a vector, how do you construct a vector? Well, the gamma matrices have space-time indices. So that is suggestive. And it actually turns out that if you sandwich a gamma matrix between a Dirac spinor and its conjugate, and it's a Dirac conjugate, it actually acts like a vector. So to show that it's actually a vector, we will need an identity. Remember that I wrote down this commutation relationship, which I said was useful for proving that the Dirac representation is actually a representation of the Lorentz group. And this was equal to I eta rho nu gamma mu minus eta rho mu gamma nu. If you look at the definition I gave of the generators of the Lorentz transformation, the fundamental representation, then this can be written as one of those generators, mu nu, and you take the rho sigma component of the generator and contract it with a gamma matrix. So if you use the definition of M, which I gave in the last lecture, you can see that this equation can be rewritten in this way. This equation, if you stare at it for a moment, you see that on the left-hand side, you have the generator of the spinor representation of the Lorentz group. And if you look at the right-hand side, you have the generator of the vector representation of the Lorentz group. This is nothing but an infinitesimal version of this very, very nice and useful formula, which is S inverse gamma mu S. So if you sandwich a gamma matrix between S and its inverse, it gives you it gives you the gamma matrix, but up to a Lorentz transformation matrix. So although the gamma matrices are constant, they do not transform under Lorentz transformation, but effectively they do, because they satisfy this identity. It's a very, very useful identity. Okay, let's move to this side. So what is this guy good for? It's good for a lot of things. But right now it's good for showing that you can construct a vector out of spinors. So if you now take psi bar gamma mu of psi and do a Lorentz transformation, then we would get this S inverse. Gamma 5 is just a constant, sorry, not gamma 5, it's a gamma 0. Gamma mu is just a constant matrix, so it doesn't change. And psi picks up a factor of S. But using that identity, we can rewrite this as, and thus we see that this thing transforms as a vector. However, under parity, you can show that this guy transforms, the zeroth component doesn't change, but the spatial components pick up a minus sign. This is what you expect from a usual space vector, right? The spatial components, when you reflect it in a mirror, should flip. That's why it's called a vector. In physics, there are these other vectors known as axial vectors or pseudo-vectors. Can someone give me an example, a very familiar example of an axial vector?
Angular momentum.
Angular momentum. Because angular momentum is r cross p, both r and p pick up minus signs when you reflect them. But therefore, the angular momentum itself doesn't change under parity. So can anyone guess how can we construct a pseudo-vector or an axial vector? There's a cross product in 3 dimensions. Yes, you're right. And but we want to construct a 4-dimensional vector. Yeah, that could be if you take 2 vectors and you could. Would a wedge product to 2 vectors? They would not give you a vector in 4 dimensions, right? Because they would give you a rank 2 tensor. It's only in 3 dimensions that the wedge product is actually dual to the epsilon tensor gives you another vector, right? It's an accident of 3 dimensions. So in 4 dimensions, you can construct an axial or pseudo vector by using gamma 5. So you had gamma mu. If you just put a gamma 5 here, you can show that, again, under Lorentz transformation, the gamma 5 does absolutely nothing because, the S's commute through gamma 5, right? But if you do a parity transformation, then the 0th component now picks up a minus sign, whereas the spatial component do not pick up any signs. And this is how, in 3 dimension, an axial vector or a pseudo vector should behave, right? And that's why we call this an axial or pseudo vector. Okay, time for the real topic that we want to discuss today, which is writing down Lagrangians for spinors.
Can I ask a quick question?
Yeah.
How did you commute the S inverse through the gamma 0?
Oh no, I mean that's how.
Oh yeah.
That's how the psi bar transforms, right? Yeah. So we want to construct Lagrangians. So let's first try the kinetic term. So we want all these terms to be invariant under Lorentz transformation. So a kinetic term should have a derivative, space-time derivative, right? So let's try this thing. You know that these guys, this actually transforms like a covector. A covector is, I think Neil told you about covectors and vectors, right? So, and the rest of these guys, psi bar, gamma mu psi, that transforms as a vector under Lorentz transformation. And therefore, this thing transforms as a scalar. Okay? So if you do the transformation from this guy, you would get the inverse of the Lorentz matrix. And from this guy, you would get something like this. And then they would give you delta nu rho. And then you'd see that this is actually invariant. Okay? Do you want me to show this calculation? Okay, let's just do this because, save some time, right? So we have psi bar, gamma mu, delta mu, because this is a question I'm going to ask you in the interview, so it's worth doing. So this goes like I psi bar S inverse. Gamma mu doesn't change. The derivative operator becomes mu rho, delta rho. And then psi becomes S of psi, right? But these S matrices are constant matrices, right? They do not depend on space-time points. Lorentz transformations are constant. So So we can commute this guy and this guy. So now look at this thing and this thing and this thing and apply our favorite identity. Then we should get I psi bar mu sigma, gamma sigma. You get this from these three things, but there's already another one. Now this guy and this guy are inverse of each other, so they give you a delta function, and that delta function sets this index and this index to be the same. So you get, okay? So our kinetic term is I times d4x psi bar. You might say, why do we need this I? This I ensures that if you take that, so let's say K, kinetic, this I ensures that up to total derivatives, this is actually real, the action. This is important because when we quantize the theory, the action, we will derive a Hamiltonian from the action. If the action were not real, the Hamiltonian would not be Hermitian. Okay. All right, so next, let's talk about the mass term. So before we talk about the mass term, let's talk about the mass dimension of our Dirac spinor. So as you know, in natural units, which are the units we are using, the action is dimensionless. So the measure of integration of the kinetic term has the mass dimension of -4. The gamma matrices are just constant numbers. They are dimensionless. The derivative operator has dimension of +1. So putting it all together, you can derive that the dimension of psi, which must be equal to the dimension of psi bar, is 3/2. This is a very dimension-dependent dimension, meaning that this is in 4 dimensions, this is 3/2. In higher dimension, it will be different. Okay? But using this argument, you can always figure out what the dimension is. Okay. So this means that if we write the mass term to be proportional to psi bar psi, or at the coefficient, which let's call it m, the dimension of m is fixed to be 1. Okay. So now, so the Dirac Lagrangian is Lorentz invariant, and it's given by psi bar where delta slash is this notation, and it was introduced by Feynman. It's a contraction of the gamma matrix with some covector. All right, so I probably won't get to Majorana spinors today, but that's all right. Let's construct the Lagrangian for a Weyl spinor. Okay. Unfortunately, I'll have to cover this blackboard. I hope that's all right. You can read about Majorana. If we don't get to Majorana spinors, you can read all about it in the lecture notes. And come and ask me questions. Okay, Lagrangian for Weyl spinors. L for while. Again, we can use the connection with Dirac spinors to derive everything we need. So the Lorentz transformation matrices in the while basis will take some block diagonal form, and let's call it SL and SR. So these blocks are all matrix SL2C elements. You can show that. Because we wrote down the explicit expressions for SL and SR. Remember, SL is exponential of minus beta dot sigma plus I theta dot sigma divided by 2, whereas SR is just this sign. It's just plus sign over here. Okay, and you can see that these are traceless matrices, right? So so the determinant of this thing is going to be 1 because the generators are traceless. Okay? So that shows that they are SL2C matrices. So using the fact, my favorite identity, one can now derive that a sigma matrix sandwiched between SL inverse and SR is going to be this thing, whereas a sigma bar matrix you can derive this from here, of course, the bar here. Okay? And you can also then show, we already know this, but let me just write it out anyway. Chi L goes to SL of chi L. Psi R goes to SR of psi R. However, psi L dagger goes to, chi L dagger goes to chi L. This is SR inverse. So this and this, this follows from the fact that psi bar goes to psi bar S inverse, but inside psi bar there's a gamma 0. Right? This is equal to psi dagger gamma 0 of psi inverse, and psi dagger is chi L dagger psi R dagger gamma 0 S inverse. So if you now multiply with gamma 0 has this identity matrices in the off diagonal elements. So that'll flip these two guys. So, right? So using this, you can show that psi L dagger transformed with SR acting on the SR inverse acting on the right, and similarly, psi R dagger okay? So now using this, you can now re-express the kinetic term for the Dirac Lagrangian. So let us re-express the kinetic term for the Dirac Lagrangian in the while basis. So L Dirac kinetic I psi bar gamma mu. This thing becomes a kinetic term for the left-handed while spinor, which comes with sigma bar Often this is omitted, the L, so you'll have to figure out whether it's left-handed or right-handed from the bar. And then there'll be another term, psi r, dagger, sigma mu, delta mu, psi r. Now using these guys, I guess these guys as these guys and these guys, you can show that each of these terms is Lorentz invariant. So this is Lorentz invariant, and this is Lorentz invariant. So if you want to write down the kinetic term for a left-handed valve spinner, all we need is this term. For right-handed valve spinner, all we need is this term, right? What about mass terms? So mass terms like this are not Lorentz invariant, and that's because chi L transformed with SL, whereas chi L dagger transformed with SR inverse. So you're not going, this is not going to be Lorentz invariant. So this is not allowed. If you write out the Dirac mass term, so if you write out the, say, Dirac mass term, you find that in terms of valve spinners, it's not a mass term. And this is something that we mentioned earlier. It's actually a coupling between the left-handed and the right-handed valve spinner. These terms are individually Lorentz invariant, but you cannot interpret them as mass terms for valve spinners because they just tell you that the left-hand, when there's mass present, the left-handed and the right-handed valve spinners are coupled. Okay, so you can think of the Dirac mass term as a coupling of between its left-handed and right-handed parts. So this is not to say that you cannot have mass terms for valve spinners. You can, you may, but you have to pay a price. And that's our last thing that we're going to cover today. So I'm assuming that I should be able to just use this board and maybe the next one. So valve spinners may have mass terms, and these mass terms are known as Majorana mass terms. Okay. Suppose you have a right-handed valve spinner, and you can do this for left-handed ones too. Then the Majorana mass unfortunately, Majorana died very young, a brilliant career cut short. He actually went missing. Maybe the aliens abducted him because he was so brilliant. They wanted to kind of, use him in their parameter institute for outer physics. All right, that's a bad joke. So the Majorana mass term is of this form. So you have some mass parameter. You have a transpose, sigma 2, sigma r. I sometimes write it 2 below, sometimes above. It doesn't matter. It's the same thing. Now, let's just talk about what is the price that you have to pay. The price you have to pay is that if you look at the Dirac, the Lagrangian for the valve spinner, the kinetic term, as well as the mass term, which is an interaction term, then you have a symmetry, a phase symmetry. So that symmetry, your Lagrangian is invariant. And you saw something like this in your complex scalar field. your complex scalar field Lagrangian was invariant under a global phase symmetry, and that was a reflection of the fact that the charge that you associate with the particles that you got from quantizing that field were conserved, right? So we will see in the future lecture that in the case of spinors, that's also the case. This global phase symmetry ensures that you have a conserved charge. Because the Majorana mass term, C, is not complex conjugated, the psi r, therefore, that symmetry is lost when you add this Majorana mass term. So that's the price you pay. You can add a Majorana mass term to your Weil spinor, but then charge is not conserved. Okay? And at some point you'll see, I hope not in this course, but hopefully you'll see that when you take a Majorana spinor and you quantize it, its particles and its antiparticles are the same particle. So because it's essentially uncharged. So and Majorana spinors have important applications, possible application in solar neutrinos and stuff like that. So physics beyond the standard model. Okay. So I claim that this is actually invariant under Lorentz transformation. And to show this is done in detail in the lecture notes. What you have to do is to basically use this identity. So if you take a Pauli matrix and transpose it and sandwich it between two sigma 2s, then you get the minus of the Pauli matrices. Then you can show that this is Lorentz invariant. There's another price you have to pay for Majorana spinors, for the Majorana mass term. And if you actually write out these two-component spinors in terms of its components, sigma 1 and sigma 2, then you can show that the Majorana mass term has this form. So there is a proportionality which means that if psi 1 and psi 2 commutes with each other, this is 0. So for the Majorana mass term to exist, it cannot be true that the two components of this Weil spinor can commute with each other. In fact, in the next lecture, we shall see that inspired by the spin statistics theorem, when we quantize a spinor, the quantization condition will have something like we will have to use anti-commutation relationships. Okay? If you don't, then we will run into lots of problems. Our Hamiltonian will not be bounded from below for spinors and stuff like that. Okay? So in the classical limit, we are still doing classical physics, of course. All spinors, they are not commuting numbers. They are anti-commuting numbers. They are what is known in the literature as Grassmann numbers. They are Grassmann numbers. So they're classical, but they're anti-commuting. Okay? So you might say, how does that work? If I have a Grassmann variable, which is a function of space-time, how does this actually work? The way it usually works is that you have some function, the usual function of space-time, which is commuting, and some parameter, constant parameter, which is a Grassmann parameter. Okay? Anyway, there's a whole literature about this. This is called the, I think, body, and this is the soul, or the other way around. So you have to assume that these guys actually anti-commute. So in the classical limit, which is h equals to 0 limit, the quantization condition we'll see will actually be consistent with this. Okay? So this is the story of how you can give mass to Wald spinors. In the last minute, let me just tell you how you can derive a Lagrangian for Majorana spinors. And this will be a very brief outline, so but it's straightforward for you to verify. And the story is given in the lecture notes. What you want to do is to start with the Dirac equation. Okay, so to derive a Lagrangian for the Majorana spinor, we need to introduce the action of charge conjugation. In a tutorial next week, you will see that under charge conjugation, a Dirac spinor goes to its charge conjugate, which is defined by this thing. So you take the complex conjugation and multiply by something proportional to gamma 2. Then a Majorana spinor formally is defined as a spinor which is equal to its charge conjugate. So Majorana spinors this is also called a reality condition, because as you can see, psi c involves a psi star. So in some sense, the Majorana spinor is a real spinor. Okay? And now if I write out the Dirac spinor in the Weyl basis, then this condition connects the left-handed and the right-handed components of that. And the expression that you get is that if the left-handed component is chi, then the right-handed component is I sigma 2 chi star. So now, if you take Dirac equation and express it in terms of this Majorana spinor, then you get the Majorana equation, and this is the equation for a Majorana spinor. So this is the Majorana equation. You cannot derive the Majorana equation from the Dirac Lagrangian, because when you do the variational principle, the left-handed and the right-handed components of the Dirac spinor is no longer independent because it's Majorana. So to derive this equation, you have to use a different Lagrangian. And that Lagrangian, or action, happens to be, there may be I haven't really checked it, so this is the mass term that we wrote down, but there's actually another mass term which is needed for this okay. So this is the action for the Majorana spinor, okay? And so this is the usual kinetic term that you would expect from a Weyl spinor, and this is the Majorana mass term. Okay, so let me stop there. Do we have any questions? Sorry, I know I went very fast today, but I think, yeah?
So the symbol over X is a transpose, not dagger?
This is transpose.
Oh.
But this is a dagger, okay? Right? Any more questions? Yes.
No, in that last term there's no I, but in that last term there is an I.
Okay, there should probably an I there. It's so yeah, you should be really. Oh, that's an interesting. It should be Hermitian, right? And the thing is that sigma 2 is imaginary. So therefore, if you take the Hermitian conjugate of sigma 2 is this thing. So if you take the Hermitian conjugate of that, you get, so it's, well, sigma 2 is Hermitian, right? So I don't have to do that. So there, okay. But then what happens is it will also reorder the components of these things, right? They will exchange those things. So I think there would probably be a minus sign coming from that. So I think there should be an I sign to I to kind of get to compensate for. But let me confirm that. Okay, thank you. All right. Any other questions? All right, let us not keep our friend waiting then. Thank you. I'll see you guys in tutorial today at 2.